Hello, namaste everyone. Hope all of you are well. And today we are going to discuss something new, except from all that 6 chapters, some basic concepts of chemistry, atomic structure, classification of elements and their periodic properties, chemical bonding, states of matter, thermodynamics. Except this sixth lesson, we are going to discuss something else. When we are studying in the class 10, that time, the teacher has taught us about the reaction, what is chemical reaction. In any chemical change, the representation of elements in the symbolic way, you know very well when there is a chemical change. Chemical change means you know very well that reactant will change into a product, right? So here, to represent this, we write in a symbolic way, that is called chemical reaction. After that, we have studied about the types of chemical reaction in class 10, and we have also discussed about the states of elements, in which physical states they are. So there are many types of reactions, but on the basis of something, basis, as for example, if I talk about on the basis of physical states, on the basis of heat, on the basis of speed, the reactions are of different types. If I talk about on the basis of physical states, right, on the basis of physical states, the chemical reactions are of two types. On the basis of physical state, physical state means you know very well solid, liquid and gas. If I talk about on the basis of physical states, the chemical reactions are divided into the two types. First is homogeneous reactions. You may have heard this homogeneous word in the mixture, right? Now I am teaching you in the terms of reactions. And heterogeneous reactions. What is the meaning of this homogeneous reactions? Homogeneous reactions means the reactant and product, they both will in the same physical state. As for example, if I talk about the reactant is in solid, then the product will be also in solid. If the reactant is in the liquid state, the product will be also in the liquid state. If the reactant is in the gaseous state, then the product will be also in the gaseous state. You know very well there are so many reactants and so many products can be formed. Either if I talk about the combination reaction, decomposition reaction, displacement. So the reactant can be two also, more than two also, and product can be one, two, more than two also, right? So here when the reactants are in the whatever physical states and the product are also in the same physical state, then that type of reaction is called homogeneous reaction. And if I talk about this heterogeneous, then in the heterogeneous, just think about there are two reactants, one is in the solid state, another is in the gaseous state. The product will be also in the gaseous state and solid state. Means when two or more than two reactants form one or two products, they will be in different physical states. So this type of reaction is known as heterogeneous reaction on the basis of physical state. If I talk about on the basis of speed, right, on the basis of speed if I talk about, then there are two types of reaction. First is fast reaction and another is slow reaction. So if I talk about fast reaction, in this fast reaction what happens, especially these are being formed in the ionic states, ionic compounds. If I talk about the sodium chloride, so here the rate of reaction, it's impossible to, not impossible, but it's very difficult to determine that what is the rate of reaction in the fast reaction. It's very fast, rapidly. So here on the basis of speed, the reaction, fast reaction, it's difficult to determine the rate of reaction. In the slow reaction, if I talk about the Just suppose here hydrogen gas is there and iodine gas is there. They both form HI. Here it's called molecular reaction. It's also known as molecular reaction. So here it's easy to determine the rate of reaction. But if I talk about here NaOH and HCl, it gives you NaCl plus H2O. So here the rate of reaction is difficult to determine. So it's called ionic reactions also, ionic compounds and ionic reaction, and these are molecular compounds. Molecular compounds, and the fast reactions are ionic compounds. So this was on the basis of speed. If I talk about on the basis of heat, on the basis of heat, on the basis of heat also there are two types of reaction. One is exothermic reactions, and another is endothermic reactions, right? You may have heard about these all the things in the previous chapter of them. Why I am teaching this all, I will come to the point. In this exothermic reaction, when the reactants are in the reactants, afterwards the reactant form product. So after forming the product, they release the gas in the forms of X kilocalorie. Just suppose this is the amount of heat which is evolved after giving the product. Means the heat is coming out. So this type of reaction is called exothermic reaction. And if I talk about endothermic reactions, so here heat is involved. Means to form here, if I talk about to form this product only, so reactant will absorb the heat. Here, just suppose that X kilocalorie heat is absorbed here, and then the product is formed. So there are two types of reaction on the basis of heat and on the basis of direction. On the basis of direction, if I talk about, there are also two types of reaction. One is reversible and another is irreversible reaction. Reversible and another is, just suppose the second one is irreversible. So there are two types of reaction on the basis of direction. Now you can ask me, sir, here can one reaction be fast reaction also and homogeneous also? Can one reaction be this both? Means according to the physical state also, according to the speed also, according to the heat also, and according to the direction also. Can one reaction be formed? Yes. In one reaction, see, one human being has a lot of properties. You just suppose. We judge according to the any basis, right? As for example, if I want to judge you, teacher judge students by the knowledge, IQ levels, yes. But it doesn't determine that if his IQ level is low, so in the activity also his IQ level, he know how to play cricket very well. He doesn't have a knowledge of bookish, but he know very well how to dance, he know very well how to do karate, he know very well how to play football. So on the basis of something we determine. Similarly, if an intelligent student, his IQ level is very high, he plays also cricket very well, he do dancing also very well, he sings also very well. So one student can have a lot of properties. Similarly, in the reactions also, some of the reactions has many. In the reversible reactions, the reactant can be converted into the product, and this product can also be converted into the reactant. This is called forward reaction and this is called backward reaction. Means if I talk about this product, then it is not 100% completely the product is not formed, because it is a reversible reaction. It can come back again into the reactant. So that's why I have told you here in the reversible reaction and irreversible. Irreversible means only after forming the product. Now this product can't be changed into the reactant. So now one question is that in this is the main topic of today's chapter, the reactant into product and product into the reactant. That's called reversible reaction. They are having a equilibrium state. If I talk about the equilibrium state, if anybody will ask you, sir, what is this equilibrium, or if you talk about this equilibrium state, the system means, if I talk about the reactant which is converted into the product and product is converted into the reactants, means they are having both the sides direction. Here it is in the forward direction also and in the backward direction also. If I talk about where they are from, they are possible only in the containers. They can attain the equilibrium state, means there will be one state, means when the reactant is going to become product and when the product is going to become the reactant, so there will be one state, and that state, when both are going to become, either reactant is going to become product or product is going to become a reactant, that state, when it change either in the backward or in the forward, so when that state is that state is called equilibrium state. What is that state called? Equilibrium state, when the reactant is now going to convert into product or product is going to convert into reactant. That state, when they reach to that level, when the reactant is going to convert into the product or product is going to convert into the reactant, so that time, just I am giving you a reaction, when hydrochloric acid and ammonium hydroxide, okay, when these both two reaction, they give you ammonium chloride, NH4Cl and H2O. So here again this ammonium chloride can be converted into the ammonium hydroxide and hydrochloric acid. Why? So this is a reaction which is called equilibrium reaction, chemical equilibrium. Today's our main topic is chemical equilibrium, right? So to understand this equilibrium state, I have given you these all the examples, how many types of reactions, how many types of this forward, backward, when the reactant change into the product, when product change into the reactant. That was the main thing to make you understand. Now after this, you know very well, when this reactant convert into the product, there is a change in concentration. Means whatever the reactant state was there, that state, I'm not talking about the physical state, I'm talking about the concentration. If you don't know about the concentration, then I will make you to understand about the concentration also. First of all, to understand the rate of reaction, as I have told you, in the fast reaction, there is impossible to determine in the ionic compounds what is the rate of reaction, because it is a fast reaction. And in the molecular reaction or molecular compounds, when they form, there is possibility to make you understand about the rate of reaction. So if I talk about the rate of reaction, if I were to tell you what is this rate of reaction, then rate of reaction is equal to plus minus. Plus minus means here the product will get something, product will get some rate. So that's why here if I talk about the plus minus, then there will be change in product, there will be plus, and the change in reaction concentration, there will be minus. So that's why I am talking about plus minus. Change in concentration, upon whatever the time has taken to change, means rate of reaction is plus minus change in concentration upon time taken to change. You know very well, here just suppose A plus B, these are the two reactants. When this reactant convert into product, C plus D, so here A will lose now. So that's why here the reactant side, there will be minus, and the product side, since they are becoming, that will be product. So if I talk about in this chemical equilibrium reaction, the concentration of A, as for example, minus dA upon dt, means time taken to change, and the concentration of the reactant has been decreases. If I talk about the B also, then there will be minus dB, the concentration upon the time taken to change. If I talk about this product side, then there will be plus dC upon dt, and there will be plus dD upon dt. Why I am telling you these all the things here, as this is a chemical equilibrium, the reactant concentration decreases and the product concentration increases. I will tell you why the rate of reactions here. If I talk about here, there is a rate of reaction R1 and here there is a rate of reaction R2. Then since in the forward direction there will be a plus in concentration, and in backward direction there will be a minus in concentration, means rate of forward and backward. You must understand initially the reaction occurs in the forward direction. in the starting time, the reaction occurs in the forward direction, but as the concentration of the product increases, reaction also start in the backward direction. That's why these reactions are called chemical equilibrium reactions. So at a certain stage, this forward reactions becomes equal to the rate of backward reaction, and that state is called equilibrium state, and our chapter name is chemical equilibrium. So I will show you one graph also. What is this rate of equilibrium at the equilibrium state? What is the reactant and what is the product? Each and everything I will show you in the graph, that how these reactions are converted into the product. So our today's topic is chemical equilibrium. Hope all of you have understand why I have taught you these all the things. These things because you must know what is equilibrium state. These all are not so much useful, but to make you understand, these are useful. So whenever you are learning something, you must get the basic concept, means from the back side, from wherever the term has been started. I have taken it from that side, and I hope that all of you have understand also this chemical equilibrium. So our today's main topic is chemical equilibrium, and this equilibrium, as I have taught you about both the equilibrium state, that how the reactant and product is being converted into this equilibrium state, right? So let's go ahead now today. After understanding these words, that reactant and product. So here, if I talk about at the equilibrium state, the rate of reaction is equal to the rate of reaction at equilibrium state. What happens? I'm just showing you at the equilibrium state. The rate of forward direction becomes equal to the rate of backward direction. Means here you can write the rate of forward direction becomes equal to the rate of backward direction. Why I have teaching you this all? This is the main thing, that equilibrium state. You must understand there is a certain stage when the product concentration increases, and as the product concentration increases, they start changing into the backward direction, and a times come when there is an equilibrium state. If you want to see this graph, then I'm just showing you that just suppose here concentration and the time. Here if I talk about in the x-axis and y-axis, the rate of reaction and the time has taken to change. So you can write here the rate of reactions and here time taken to change. Just suppose. Okay. Now there are two reactions, forward reactions and backward reactions. So just suppose that here there is a forward reaction. This is forward reaction. Okay. And this is backward reaction. So this state, when they both start changing, in this state means this forward and backward reaction. Okay, so in this forward reaction and in this backward reaction, a time comes when this product concentration start converting into the backward. So this state here, if just suppose this is your R1 and this is your R2, so at this stage R1 is equal to R2, and that is called equilibrium state. Which state it's called? Equilibrium state. So if you want to know more about this equilibrium state, we will move towards in this chapter only. What are the characteristics of this equilibrium? So here, as I talk about the characteristics of the equilibrium, the concentration of the reactants and products do not change with the time. The concentrations of the reactants and product do not change with the time. At the stage, the number of moles of substance is produced per second in the forward reaction is equal to the number of moles of substance which disappear per second in the backward direction. Chemical equilibrium is dynamic in nature, that is, the reaction although appears to be stopped, but they actually take place in both the direction with the same speed. So that's why the chemical equilibrium, we can't say that reactant has been disappeared. So that's why here the chemical equilibrium is dynamic in nature. Chemical equilibrium can be approached to both the sides, reactant side also and the product side also. At equilibrium, each reactant and product has a constant concentration, and this is independent the fact whether the reaction starts from forward direction or backward direction with the reactant or the product. Equilibrium is not affected by the presence of catalyst. The catalyst only helps in attaining the equilibrium rapidity. The measurable properties of the system like temperature, concentration, color, density, etc., they don't undergo any change with the time at the chemical equilibrium conditions. Homogeneous equilibrium is the equilibrium in which the reactant and products are in the same phase. Heterogeneous equilibrium is the reaction or equilibrium in which the reactant and product are in the two or more than two phases. So these are the characteristics of the equilibrium. Hope you have understand about the equilibrium, what are the properties of the equilibrium, characteristics of the equilibrium. Now I will go through the molarity or concentrations that call active mass. So hope all of you are understanding the concepts that whatever I am teaching you, because these are all the things whenever you are reading any notes about the chemical equilibrium, that time you will get the knowledge. Yeah, so that's not really a good thing that we should understand these things very politely and very nicely. Now the new term is active mass. Have you heard the word active mass? I hope all of you have heard about this active mass. If you have not heard, then also not an issue. If I talk about the active mass, means the term active mass means the concentration of the reactants expressed in mole per liter. That's called molar concentration. Molar concentration, all of you know very well, right? So molar concentration, or if the pressure of the reactant gas in the atmosphere in case of gases and solution, the molar concentration means the number of gram molecules present per liter. If number of gram moles of the substance by volume in liter, number of gram moles, number of gram moles. Why I am writing this gram moles? I hope I have taught you in some basic concepts of chemistry. Number of gram moles of the substance, number of gram moles of the substance by volume of solid, or volume in liter, directly understand, volume in liter. Okay, so remember the word, this active mass. If you want to write, if you want to convert this gram moles of the substance, that is weight of the substance in gram by molecular weight, weight of the substance by gram in the molecular weight, this number of grams of moles of substance, that is weight of the substance in gram, weight of the substance by gram, weight of the substance in gram by molecular weight into volume in liter. So you have understand here that what is number of grams of substance, that is weight of the substance in gram by molecular weight. So you can write here, if this volume is given in milliliter, then no need to worry, you can definitely convert. Just suppose that the volume is given in milliliter. Okay, so you know very well that here weight of the substance in gram by molecular weight into, if volume is given in milliliter, okay, volume, so you have to divide by the 1000, so this 1000 will go up. So here when the volume is in milliliter, that time, okay, so here the formula of the active mass will be weight of the substance in gram upon molecular weight and You have converted this volume into the liter. It was given in milliliter, but now you have converted this volume into the liter. When it was given in milliliter, that time, that's why I have written here milliliter, and I have taken the upward. Now, if anybody will ask, what is this molar concentration? You know what is molar concentration? The same thing. Here, by weight of the substance in gram by molecular weight is also known as density. You know? Yeah? It's also known as density. So here, density of, what is density? Mass by volume, right? So here, just suppose this is the mass and this is the volume. Molecular weight, just suppose mass by volume. So here, weight of substance in gram is your mass and this is volume. So here, can we write the density upon molecular weight? Molar concentration is also known as density. Here, molar concentration is equal to, you know very well here, as I have told you, mass upon volume is density upon molecular weight. Right? Density is represented as rho and this molecular weight. Can we write this or not? Tell me. And if this is represented in that milliliter, then you have to just multiply by the 1000. So the molar concentration is equal to density upon molecular weight into 1000. So gram per liter. Gram per liter. And you will ask what will be the SI unit. So active mass is density of the substance by molecular mass of the substance. Hope all of you have understand about the concept called active mass. If you have any doubt related to this active mass, then you can drop your doubt into the comment box section. Right. Now, I will talk about the law of mass action or law of chemical equilibrium. So the first person who had given the law of mass was Gulsberg and Weig. Gulsberg and Weig in 1864, they have given the law of mass action, and it states that the rate of chemical reaction is directly proportional to the product of active mass. Rate of chemical reaction is directly proportional to the product of active mass of the reacting substances raised to the power equal to the stoichiometric coefficient in the balanced chemical reaction. If you want to derive the equilibrium constant, then I am just showing you that how to write this. I hope all of you have understand about the active mass. Now we will talk about the concentrations, whatever the Weig has given in 1864. Just suppose here that the chemical equilibrium A plus B, chemical equilibrium C plus D. But here, if I talk about the reversible homogeneous reaction in the equilibrium particular temperature, here just suppose that here it is M1 molar concentrations M2, and here it is N1 and here it is N2. Okay, is there any doubt? Now the active mass of A, B, C and D, A, B, C and D, can you tell me what will be the active mass? Active mass, if I talk about that, here it will be A, concentration of A, concentration of B, concentration of C and concentration of D, the active mass, if I talk about the active mass. Now this, according to the mass action, the rate of forward direction. Now what will happen? According to the rate of forward direction, it's directly proportional to the concentration. So here R1, this is your R1 and this is your R2. Okay. So here if I talk about R1 is directly proportional to the concentrations of the reactant. Here M1 and here M2. And if I talk about this product, then similarly, it is directly proportional to this. Have you understand what I have written here? Here I have written the mass action, the rate of reaction is directly proportional to the product of the active mass of the reacting substances. So here in the forward direction you have seen that R1 is directly proportional to the concentration of A and B, and in the backward direction RB is directly proportional to C and D. Now here if I talk about, since we remove the concentration, right, if we remove the concentration, then we put a constant, right, in the forward and backward direction. So if I just suppose this is the forward direction, so if I remove here, so R1 will be, just suppose this is the forward, so concentration of forward A and 1, B and 2. And if I talk about R2, then this is the constant of backward direction, C to the power n and D to the power. So here it will be M1 and here M2 and here M1 and here M2. Just see this reaction, then you will understand the concept, right? So here Kf and Kb are the forward and backward rate of velocity constant respectively at the equilibrium state. Now if I talk about they both are equal, if they both are equal means here when they are in the equilibrium state, right, when R1 is equal to R2, when R1 is equal to R2, what will happen? Here Kf into the concentration of M1 and B M2 is equal to Kb Cn and D and 2, right? So here Kf by Kb is equal to concentration of the reactants upon concentration of the product. And here if we put a constant is equal to the concentration of the reactants upon the concentration of product. Concentration of the reactants upon the concentration of product. Are you understanding or not? First tell me this thing. So here you can see here what is the value of K. If anybody will ask you what is the value of this K, so where K is this Kf means forward direction constant and backward direction constant. K is known as equilibrium constant and it has a definite value for every chemical reaction at a particular temperature. So the equilibrium constant at a given temperature is the ratio of the rate of constant of forward and backward reactions. Are you understanding? So here in the concentration, you can see here for the reaction if we talk about, and the product if we talk about. So here K is the equilibrium constant, where K is equilibrium constant. See, there is nothing to worry. You must understand this concept. So here what I have just written here, just suppose this is the concentrations, power, number of moles, and here these are reactant and that is product. When the rate of reaction is R1 and R2, when these both the reactants become equal, then that state is called equilibrium state. And in the equilibrium state, now here you can see the concentration of reactant is equal to the concentration of product. So here, as I have told you, the main thing is this both the reactants are directly proportional to the concentration of the reactants and products. So here the state when they both are equal, R1 is equal to R2, that time you know very well what will be the value here. That's why I have written here this K is equilibrium constant, where K is equilibrium constant. Now you can ask me, sir, if we want to write Kb upon Kf, then what will happen? Right? It's very easy. Forward direction and then backward direction. Right? Oh, sorry, here that was a little bit. So here just you can write here. Sorry, here you can see here that Kf is equal to, so C will go up and D will go down. Right? C will go up, means here the concentration of the product is upside and the concentration of the reactant is downside, right? No problem. See, Kb forward direction upon the backward direction. So here the concentration of the product and upon the concentration of the reactant. Upon the concentration of the reactant. So here you can see that where equilibrium constant is the ratio of forward and backward direction constant. Hope all of you have understand this lecture. In this lecture 1 we have discussed about what is the equilibrium state and what is the rate constant. Here you should know the SI unit of this concentration is mole per liter. Remember, SI unit will be mole per liter. This equilibrium constant SI unit, that is mole per liter. Okay, so remember the words, whatever you are getting to learn. These are the questions when we ask you. In ideal gas equation, I will show you that what are this concentration, how they are going to change, how that PV is equal to nRT, P is equal to nRT upon V, N by V into RT. Now active mass, N by V is the active mass into RT. So this active mass will be converted into this reactants concentration, product concentration. So the concentration of the product upon concentration of the reactant. I will show you these all the things into the next video. That's all for this video. I hope that all of you have understand this equilibrium lecture number 1. That's all for today, students. If you have any doubt related to this equilibrium, then you can drop it down into the comment box section. That's all for today. Thank you very much. If you have enjoyed this video, then don't forget to like and subscribe the channel. That's all. Thank you.